Recording in progress.
All right. Hello, everybody. Welcome back to our continued conversation about thermodynamics. So when we saw each other in lab this week, we did a quick review of things like enthalpy, total internal energy, heat, and work. And then we introduced this idea of spontaneous processes. And we concluded lab that day by arriving at this idea that if we were to use the idea of heat, meaning like purely thinking about is thermal energy or exothermicity enough to make something spontaneous, we found that no, it's not. There's something else going on energetically in our system that's allowing things like ice, which is an endothermic, ice melting, which is an endothermic process, to happen spontaneously at room temperatures. So let's talk about this kind of like driving force of disorder. And this is what we've called entropy. So in order to understand entropy, we need to start by looking at the second law of thermodynamics. So the first law of thermodynamics stated that energy can neither be created nor destroyed, only it must be conserved, meaning it can only be transformed from one type to another or transferred from one body to another. And in the second law of thermodynamics, we are going to zoom out of a system and we are going to look at the universe at large, which is every possible chemical and general mechanical thermodynamic system that could be crafted, summed in total. So, by definition, the second law of thermodynamics is one that we've probably encountered on our own. And like a real general way to state this is that the second law of thermodynamics says that energy will always flow from a more concentrated state to a less concentrated state. So this is kind of analogous to osmosis, right? Water will always flow, but in the reverse, right? From, yeah, more concentrated, or less concentrated, more concentrated to dilute. And it's the same idea in the sense that like systems don't like to exist in this like highly concentrated form. And here we're talking about like a concentration or like density of energy. Like the energy gradient would be quite dense. So this is like the general language for the second law of thermodynamics. Some examples of this is we can think about the flow of heat. This always flows from a high temperature to low temperature spontaneously. You leave your hot coffee out, that is eventually going to cool. And then we also have this new term that we can define that allows us to reframe this second law into something a little less general and a little more quantitative. And this is the idea of entropy. So entropy, capital S. So entropy is a measure of the amount of disorder in a system. So if we think about like processes that are driven by entropy, we have this example here on the left where we have a solid salt and water, which then get mixed to form solution. So we can see that there was a lot more ordering of our molecules pre-mixing, and then post-mixing, there's just generally a lot more chaos in this system. So we would say that this is less entropic. And the state of solution has higher entropy. Another example down here is this reaction. So we have this chemical reaction like so. And we can ask ourselves, what is it that makes this something that drives more disorder? So if we think about like just the total number of particles in this reaction, we start with 2 moles of reactant. These are all in the gaseous phase. And then I wind up post-reaction with a mole of this gas and 2 moles of hydrogen chloride gas. So then I have 3 moles of product particles. This change going from fewer moles of gas to more moles of gas is one that is a entropy-driven change in the sense that I have less disorder or low entropy on my reactant side compared to the higher amount of disorder or the high amount of entropy on my product side. I've made more gaseous particles, so thus I have more disorder in my system, right? Gases are things that exist in a highly entropic state. There's a lot of chaos or disorder in the gaseous phase compared to things like the liquid phase. So if I've got more gaseous particles, then I've got more total disorder. And then if we really want to zoom out and get universal, let's look at the Big Bang. So here is like an approximate timeline of the universe. We start at the Big Bang and see this like immediate period of inflation. And notice that all of the matter and energy from this Big Bang has dispersed through space-time outward, meaning we have less energy concentration at the Big Bang, more energy concentration at the Big Bang, and over time, that energy, that matter, all of that is being spread out throughout the universe, which is why people suspect that we might have a universe that undergoes a, quote, cold death. So the Big Bang resulted in an increase in entropy of the universe. In fact, this idea about the entropy of the universe increasing is another way of expressing the second law of thermodynamics. So instead of thinking about generally that energy will always flow from a more concentrated state to a less concentrated state, we can now state the second law of thermodynamics with a little mathematical, rather elegant statement, which says that over time, the change in the entropy of the universe must always be increasing or be greater than 0. So this is the expression of the second law of thermodynamics that we are going to operate in or with, purely because it allows us to relate this idea of energy not wanting to be concentrated to the idea of entropy. So if we're talking about, like, I think we have the discussion about how is life possible if all of life seeks to like create order within its own system. Again, the answer to that question was life is able to happen because while like living cells create a lot of order within themselves, as a result of doing so, they create more disordered environments or surroundings around them. So systems can be more ordered, right? We see that all the time in chemical reactions, like formation of a precipitate. So we can have like reactions or systems that on a micro scale will decrease the amount of chaos. But on the macro scale, those are only thermodynamically allowed according to the second law of thermodynamics because they have, as a result, net increase the amount of entropy or disorder in the universe. So this is like a conceptual understanding of the second law of thermodynamics. And again, it really zooms us out when talking about like a thermodynamic property of the universe. However, in a chemistry class, right, we are not necessarily thinking about every single piece of matter and energy associated with it in the entire universe, right? We are trying to look at something like this example here, where we're considering a very particular chemical reaction, or even something like this here, looking at some kind of like chemical change or a change at the molecular level of a substance, like dissolving it or undergoing a phase change. So in our next slide, we're going to talk about how we can justify this macro representation of the second law of thermodynamics using the microscale perspective that chemists employ when we look at things at a molecular level. So let's talk about statistics. So as it turns out, the tendency toward chaos is something that is like just a question of being statistically favored. So let's talk about it. So let's define an energetic microstate. So if we treat a chemical system as an ensemble or a population of particles, molecules, electrons, atoms, whatever, then each individual particle has a unique energetic microstate. In other words, some like energy state that describes it. And in general, the larger the system, meaning the more particles, the more possible number of total microstates exist. So I think we looked at this together on Tuesday, but let's look at it again. In this example, we've got two different gas molecules that are separated in a closed glass, like dual bulb system separated by a stopcock. And if we were to open the stopcock and think about like how possibly these blue and green gas molecules could organize themselves, arrange themselves, aka what state they would be in, we found that in a very simplistic kind of reduction of this system, there could be four possible microstates. So we have the state where both are on the left, green is on the left and blue is on the right, blue is on the left and green is on the right, and both are on the right. Now, again, I think this diagram is being a little bit lazy in the sense that it is showing, I guess it's showing here equivalent positioning here, but like notice this is the same kind of height in the tube. So I would argue there are more microstates that we could craft from that. But if we think about like what this means in terms of entropy, if we have more microstates, then we have more entropy, right? Because let's look at over here an example of like looking at the total amount of like possibilities you could have when you have die that are rolled. So we have a 6-face die. And we can see that statistically, looking at this kind of like curve of possible results, right here in the middle of this distribution of most likely results, we see that the dice with the highest number of microstates yields a higher statistical likelihood of existing. So what does this mean for our particle ensemble? This means that we can define entropy at a molecular level as being a function of microstates. So S is equal to K times ln of W. So K is a constant. This is called the Boltzmann constant. This has a value of 1.8 or 1.38. Gotta reference that. 1.380 times 10 to the negative 23. Joules per Kelvin. W is our quantification of number of possible microstates. In the system. And then that means S is a measure of the entropy of the system. So my point in showing you this slide is to say that like this second law of thermodynamics, where the entropy of the universe has to always increase, that's what the second law of thermodynamics is one that is supported by the nature of statistics. If I have particles, right? Think about every single particle in the universe. I have an unfathomable amount, right? Like an near infinite amount of particles of mass, right? Of matter in the universe. And if I were to try to think of every possible way each of those individual particles could be arranged in 3D space with some amount of kinetic energy, with some kind of vibrational energy, with some kind of chemical potential energy, with anything, right? If we're talking just about like radiation, how much electromagnetic energy something possesses, that would result in a huge amount of microstates, right? A huge amount of chaos. And the reason we see this is because the more particles you have, the more number of microstates you have, the more that this state, where your microstates are maximized, is going to be expressed statistically in nature. So, for example, if I were to consider this system, but then rather add instead of just 2 particles, 3, then I would be increasing my microstates by a fair amount, which means that I would expect for this system of 3 gas particles to be one that is way more entropic, just because combinatorically, statistically, I have more microstates and my system's going to tend to favor, on average, that system, right? That amount of entropy, that amount of disorder. So this is a way for us to calculate the entropy of like a molecular ensemble based on, the number of microstates and statistics. And we could do that. However, this is something that you will probably do in your upper division chemistry courses if you take them, or even your graduate level STEM courses called statistical mechanics. This is where we do, in fact, treat our particles like a statistical body of objects. But for Chem 220, it's enough to understand that like the reason why things tend toward a higher state of disorder is because statistically things with more microstates are expressed more in a Gaussian curve. So there's a statistical backing for the second law of thermodynamics. Now, let's talk about entropy in general. Like we've got kind of like 2 different sides of the spectrum. So like at this point, we've now seen that the change in entropy of the universe must always be increasing and that we could calculate the net entropy of a system using our Boltzmann constant and taking the natural log of the number of total microstates. So like this is a super, super large perspective of the idea of entropy, and this is a super, super micro perspective of entropy, where we're not even just thinking about particles, which is what us chemists do, right? We think about molecules, but rather we're thinking about the number of possible microstates of energy that all of those particles in a chemical system could contain. So I think it's time for us to maybe find some like middle ground here. Like, how can we express entropy in a way that is not one based on the universe at large or tiny little ensembles of particles? So in Chem 220, we will define the change in the entropy of a system, meaning a chemical system, as being equal to the change in the enthalpy of the system divided by the temperature at which that system exists. So this is how we are going to think about the entropy of chemical systems in this class. So delta S system, this is the entropy change of some chemical system as a whole. We don't have to look at all of those individual microstates. So this is going to be expressed as like S final minus S initial, which if we're talking about a chemical reaction is often going to be S product minus S reactant. Delta H of the system, our enthalpy change. Of the system at constant pressure. And since we are at constant pressure, we can think about this as being the heat that's exchanged between the system and its surroundings. And T is some set temperature of the system in Kelvin. So let's take a look at the units here. So if we measure the change in heat, right, delta H, that is often in joules, right, energy per Kelvin. So S is expressed in joules per Kelvin. All right. In our next video, we are going to look at maybe how we can reframe this, because if we think about experimentally, what could we do to determine the enthalpy of the system? That brings us back to heat of reaction and calorimetry stuff from Gen Chem 1. So we can kind of flip a sign and redefine what we call enthalpy of system with our enthalpy of surroundings. And then from there, we are going to use now this idea of entropy to answer this question of what makes a reaction or any other chemical process spontaneous. Because it can't just be entropy alone, right? Also can't just be enthalpy alone. So we're moving toward the conversation of other expressions of entropy and then why entropy matters to us when talking about spontaneity in our next video. So I'll see you then in just a moment.